Bismillah ar-Rahman ar-Rahim. Okay, my son, now we are going to solve some problems related to electric field, electric flux, and Gauss's law. I just want to remind you that this example that we are showing you are taken from all the exams, and it will give you a flavor of how are the problems of all the exam problems. I also want to remind you to don't rely only on our videos to learn the concepts. You have to yourself sit and solve other problems. So don't rely only on this set of problems. You have to go and practice yourself. So we give you the beginning, so you how to start, and then you have to do it yourself in order to succeed in this course or any other course at KFUPM. So the example, first example I want to discuss with you here is about electric flux. It says a 5.14 microcoulomb point charge, this is the point charge, is at the center of a cube. This is a cube in blue, and the charge is in red here. It is 5.14 microcoulomb. That's the charge of it. The cube has sides 0.25 meters. So these are the sides of the cube, three-dimensional. Okay. The question is, what is the electric flux through one of the faces of the cube? So you want the flux through one of the faces. Let's say, for example, this face, the upper face. Okay. And one thing is important is that this this point charge is at the center of the cube. Okay. So this is my cube here. Okay. You agree with me, my son, that since the charge is in the center, the number of lines and the strength of the electric field through each side of this cube are equal. Okay. They are the same number of, because the charge is in the center, the flux through this face and this face, the 6 faces of the cube, the flux is the same through each one of them. Okay. So he's asking about the flux through one of the faces of the cube. Let's take this face for example. Okay. So it is difficult to calculate the flux through this face, but one thing we can do is to calculate the flux through the 6 faces. Okay. I'm going to calculate the flux through these 6 faces, which is a closed surface. And we know when you have a closed surface and the charge is inside, then we take the flux is Q enclosed over epsilon 0. This is one of the equation we have seen in the previous video. So if you take a Q enclosed, which is the red charge here, which has a value of 5.14 microcoulomb, so if this is 5.14 into power minus 6, it's microcoulomb, because you have to use SI units, and you have to make sure you use a coulomb here. So 5.14 to minus 6 divided by epsilon 0, 8.85 into power minus 12. Okay, so this is the flux through the 6 faces, which is equal to 5.8 into power 5.8 into power 5 Newton. This is the flux is Newton per coulomb meter square. This is the SI units of the flux. Okay, that's the flux through the 6 faces. And I told you, because the charge is right in the center of the cube, the flux through each face is equal. They are equal. So this. If I want the flux through one face, okay, one face, I would take this flux, 6 faces, and divide by 6. Okay, so I take this number here, 5.8 into power 5, and I divide it by 6 to get 9.68 into power 4. If you do the calculation correctly, 9.68 into power 4 Newton per coulomb meter square. And this is the answer we are looking for. This is the flux through one face. Imagine he asks you about the flux through 2 faces, then you take this value and multiply by 2. Okay? This is how you would solve a problem like this. But however, if the charge was not in the center of the cube, you cannot do all this, because the flux through each face, for one face is different from the flux through the other face. So you cannot just divide by 6. Here we are dividing by 6 because the flux through each face is equal. They are all equal, the fluxes through each face. Now you might ask another question. Imagine you have now a hemisphere. Okay, a hemisphere, or and he asked about the flux through this hemisphere. Okay, because the charge You see the electric field lines crossing this hemisphere, which is half of a sphere, okay? It's like a dome, okay? Of radius r. By the way, in this problem, it gave you the length of the side. You don't need the length, okay? Because we have said that the flux is independent on the shape, okay? And it's equal only on the charge enclosed over epsilon 0. Let's return to this problem here. So he wants the flux through and the charge is right here in the center, okay? And he wants the flux through this curved surface, okay? So the way to do it is to complete the sphere. If you complete now, you get a sphere, okay? So the flux through the sphere, okay, will be equal to what? Q enclosed over epsilon 0. And Q enclosed is what? Since now we have a closed surface, Q enclosed by this sphere is the charge Q over what? Over epsilon 0. Now, if I want to find the flux through the hemisphere, okay, which is half of the sphere, the hemisphere, and again, the charge has to be in the center here, okay? In the hemisphere will be flux through the sphere divided by what? By sun divided by h by 2. Divided by 2 because you have two hemispheres, okay? So this is the first example. Thank you. So this is another example about the electric flux. It says if the constant electric field, you see here it's constant, 25 Newton per Coulomb, this is a constant number. In the figure has a magnitude, this is the magnitude of the electric field, and the direction is indicated here by the arrows, is to the right. You're asking about the calculate the electric flux through the curved surface of the hemisphere. Remember I gave you the example of the hemisphere a few minutes ago? Now this is now the electric field is coming from outside. There's no charge here in the hemisphere itself. There's a charge, of course, I'm sure there's a parallel plate here, a plate here with the positive charge which is creating this electric field uniform, okay? This is uniform electric field. You want the electric flux to the curved surface, not the flat surface. You see, this shape has two surfaces, the curved surface and the flat surface, and it's a closed surface. The surface is closed. There's there's a flat surface and there's a curved surface, okay? He gave you the radius of this flat surface here, 5 centimeters. Knowing that there is the electric field is perpendicular, as you can see it, to that surface, and there is no charge inside the hemisphere, no charge. Okay, so the electric flux is coming from the external electric field here, which is crossing this surface. Of course, that electric field is crossing two surfaces. Let me just draw for you this example here. That's the flat surface, and this is the hemisphere. Okay, all right. Of radius, this is radius r. Okay, and the electric field is crossing in this direction here. Let me draw it in green here. That's the electric field here. You can see it. Okay, it's uniform, and it is given to you. It's 25 Newton per Coulomb. Now, he wants the electric flux through this surface here. Flux through the curved, I'm going to call it curved surface. Okay, so what is the flux through that surface? Of course, we have also this, we have a flux through the flat surface. Okay, because you can see the electric field is crossing the flat surface and is crossing the curved surface. We said in the previous video, if the electric field for a closed surface, when the electric field is entering the surface, the flux is positive. When it is leaving when it is entering the surface, the flux is negative. When it is leaving the surface, the flux is positive. Okay. Now we can say that the flux net through both surfaces, the flat and the curved, is equal flux curved, okay, plus flux flat, okay, because we have two surfaces, and this is equal to Q enclosed over epsilon 0. But there is no charge enclosed in this closed surface, so this should be equal to 0. Okay, it's asking about the flux through this surface here. Okay, the question. So the flux through the curved surface, okay, is equal minus the flux through the flat surface. Okay, and the flux through the flat surface is easy to calculate because I will tell you how. Okay, The flux to the flat surface, you have to look at the vector A, okay? The vector A is like this. And the vector E is entering. You can see it here. Huh? The vector E is entering. So E and A, the angle between them is 180 degrees, okay? And E is uniform. The value of E everywhere crossing this surface is constant, okay? So I'm going to put a minus sign outside here. And then I'm going to calculate the flux not using Q over epsilon 0, using the other equation, which is integral of E dot dA. Because the flux has two equations. To define it, it's Q enclosed over epsilon 0 or integral of E dot dA. But I'm not going to put a closed surface because this is I'm talking about the flat surface, which it is not closed, okay? E is uniform. You can see it. It has this fixed value. And take it out of the integration. Integral of dA will give me the area of the flat surface, okay? And it is circular surface, so I can find the area easily. And the dot product will give me 180 cosine 180, which is minus 1. So I will have minus and minus EA, just like that, okay? Because E was uniform, take it out. Integral of dA will give me A, and the dot I can write here. Okay, let me write it in details, okay? Actually, this is A cosine 180 degrees, which is the angle between A and E. Why we take the vector A? The vector A, because this is the closed surface, the vector A is always toward the outside, okay? Toward the outside. So we have 180 degrees. And this will give me, so cosine 180 give me minus 1, with minus 1 will give me plus. So it will be E dot EA, and the area of this flat surface, it is circular, is pi r squared. Now you have to put the numbers. Don't forget there's a minus sign here, cancelling the minus sign here. So the whole thing is positive. So the flux through the curved surface, which is this surface here, is positive. And I told you, if the electric field line leaves the surface, it is positive. Entering the surface, it is negative, okay? So this is a positive value. So if you do the calculation correctly, you get 0.196 Newton per coulomb meter square. And this is the answer for our problem. You can even put a plus sign here to make sure that it is positive number, okay? The flux is positive. So let me write down this important information. So when E is leaving the surface, the closed surface, it has to be closed surface, okay? The flux is positive when the electric field line is entering the closed surface, then the flux will be negative. This is a general rule that you have to know, my son. Thank you. Another example related to electric flux. It says an insulating sphere of radius 10 millimeter has a uniform charge density rho 6 10 to the power minus 3 coulomb per meter cube. As you can see here, it's rho because we are talking about insulating, and it is a three-dimensional problem, okay? Calculate the electric flux through a concentric spherical surface. Concentric means they have the same center. The sphere and this spherical surface, they have the same center. Concentric spherical surface of radius 5 millimeter. You notice that this radius is less than the radius of the sphere. But let's draw this sphere first of all. Okay, that's the sphere. Here it is, of radius r, and the charge is embedded everywhere because it's non-conducting. So the difference between the conducting and non-conducting, for the non-conducting, the charge is distributed uniformly everywhere. You see, it's uniform charge density, which means every meter cube you have 6 10 to the power minus 3 coulomb. That's the charge. And if we go to a conducting sphere, the charge will reside on the surface only. There will be no charge inside. But here, the charge is inside and everywhere, okay? And it is uniform. That's the radius. That's our charge. And the charge here is rho. The charge density is given you is equal to 6 10 to the power minus 3 coulomb per meter cube. Okay, that's the charge density given to you. Okay. Now you want the flux through a concentric spherical surface. It's a surface of radius 5 centimeters. 5 centimeters will be here. Okay. So this is my surface. Okay. It's a Gaussian surface. Okay. The green. I hope you can see it here. I'm going to do it. Okay, like this. So this is my surface here. Okay, and it is a spherical surface of radius r. I'm going to put small r here, okay? That's the, of course, there is electric field line crossing that surface. There's electric field line crossing due to the charge which is inside here. So the electric field line are crossing, and I expect, and they are outward, I expect they are leaving the surface, I expect my flux to be, this is E, okay? I expect my flux to be positive, okay? So let's do the calculations. So what does the flux through the surface, this green surface, the green is equal to Q enclosed over epsilon 0. Okay? So what is the charge enclosed by this green surface, which has a radius of 5 millimeter? Okay, 5 millimeter. Okay. What is that flux? What is the charge enclosed by that? The charge will be rho times V enclosed. Remember this, Q, we have rho equal Q over V, and we have rho equal sigma equal Q over A, sigma equal Q over A, and we have lambda equal Q over L. So here we are dealing with 3 dimensions, so the charge is rho times V enclosed over epsilon 0. Enclosed by what? Enclosed by this green surface, which has a radius of 5 millimeter. It is inside the big surface, the big sphere, which has a charge density this, okay? So this rho is given to you, right? So rho, what is that volume? I want to know what is that volume. The volume enclosed by this green spherical sphere, okay? Green spherical surface, okay? Is 4 over 3 pi r cube. The r, the radius of this green spherical surface, okay, over epsilon 0, okay. So this will give me rho 4 pi r cube over 3 epsilon 0, okay. So if you do the calculation correctly, rho is what? 6 10 to the power minus 3, okay, is given to you, times 4 times pi times 0.05 millimeter, 0.005, okay, to the power 3, divide by 3 times 8.85 and to the power minus 12. If you do the calculation correctly, you will be able to find 355 Newton per kilometer square. And this is the final answer. Okay, that's the answer for that question. I'm going to repeat again. If he's asking about the flux through this spherical surface, okay, of radius r 5 millimeter. It is inside the spherical, the sphere of charge density. So we take only, remember, Q enclosed, we take only the charge which is enclosed inside here, okay, inside this surface here. We don't take this charge outside, okay? Okay, we don't take the charge outside. We take only the charge enclosed. You see, Q enclosed, which is V enclosed, which is 4 over 3 pi r cube. R is the small radius. Now, imagine, so the problem is over, but imagine he asks you about the flux through another surface which is outside here. Imagine how he asks about the flux through this surface of radius. Let's say it has a radius of 15 centimeters. Of course, 15 centimeters is more than 10. So my surface, my Gaussian surface is outside, and he wants the flux through this surface. I told you the problem is over. It's finished here. This is the final answer for the question in this problem. But now I'm doing something else. I'm asking about the flux through this surface here, which has a radius of 15 centimeters. Okay. So here the flux will be again Q enclosed over epsilon 0. Rho times V enclosed over epsilon 0. What is the volume enclosed where there is a charge? Do you take this radius here, 15 centimeters? No, you take the radius where the charge is there, which is the radius r capital, which is the radius of the sphere, of the charged sphere, okay? So here you take r cube over epsilon 0. And then you continue from there, my son, okay? Be careful here. You take the radius of the sphere, because from here to here, the 5 extra centimeters, there's no charge there, okay? We are talking about the charge. You see the charge enclosed. So you take the radius of the sphere, not the radius r, which is 15 centimeters. Okay? Thank you. Okay, now another example for the electric flux. You remember, you notice that we are solving a lot of problems related to electric flux, because this is a very important concept and a difficult concept for the students. This chapter on Gauss law and electric flux maybe is the most difficult chapter in the whole course, Physics 102. So we are emphasizing the problem-solving techniques and the different concepts that are involved in this course, in this chapter. So now it says that this problem says the figure shows a Gaussian surface. See, this surface is Gaussian. It is not a real surface, but it's an imaginary surface which has a form of what? Of a cube. You can see it. Okay, X, Y, Z axis. It has an edge of 2 meters. Okay, each edge is 2 meters, so the area will be 4 meters square, and so on. Okay. This cube lies in a region where there is an electric field vector given by this. The electric field has 2 components, minus 4I plus 8J. You notice that the electric field is uniform. It's uniform. There is no changes here, no X and Y. It's minus 4, but it has 2 components. One along the X-axis, which is negative, and the other one is positive J-axis. So the vector E, which is the electric field, is crossing this surface here. Okay, and he wants the charge contained in the cube, the charge enclosed inside the cube. Okay, all right. Let me now draw for you again this figure, because it's important to draw it to understand what is happening here. So I have this base. This is my cube. Okay, and I draw it like this, and this is the Z-axis. This is the Y-axis, and this is the X-axis. And I have 6 faces, okay? I'm going to give them names. And the electric field, I don't want to draw it because it's not important, but it is 2-dimensional, okay? It has minus 4 along the X-axis and plus 8 along the G-axis. It doesn't have any component along the Z-axis. There's no component on the electric field along the Z-axis, okay? And he wants the flux, he wants the charge enclosed. So I have to write like this: E dot dA, E net, closed, okay, for the closed surface. I have to write here closed for the closed surface, which is a closed surface of the cube, the 6 faces, equal Q enclosed over epsilon 0. So he's looking for this charge, the charge contained in the cube. What is the charge inside the cube, which is going to produce the flux, okay? So now I have 6 faces, so I'm going to do 6 times the integration, okay? But I'm lucky because the electric field is uniform and the area is easy to find it, okay? So I'm going to find the flux, okay, left side, flux through the front face. I call it the front face, okay? The front face. This is the front face here, okay? Look at it here. The front, this is the front and the other one in the back. The front face, the vector A, I'm going to write the electric field as it is, okay? There's no integration because E is uniform, it gets out, and dA will become A. So I have E dot A for the front face. For the front face. E is what? Minus 4I plus 8J dot, what is the area, vector area for the front face? You can see it. I told you the vector A is always pointing outside for a closed surface. So it will be along what? Along the x-axis. So it will be 4I, like this. 4I. Okay? Why 4? Because each side is 2 meters. So the area of this face is 4 meters square. I'm talking about this front face, okay? So I dot I give you 0. And sorry, I dot I will give dot product. I dot I will give you 1, and J dot I will give you 0, because dot product will give you the cosine, okay? The cosine of 0 is 1. So this will give me minus 8, okay? Newton per Coulomb meter square. That's the front face. Now I'm going to go to the back face, the back, okay, which is the face there, okay, that face there, the face in the back, okay. All right. So phi, the back, is equal again E dot A. I take the integral and I remove the integration, okay. And all this later will go here because it's cross surface, okay. So the same thing here, minus 4i plus 8j. The vector E doesn't change, but what changes is the area. So that face, the area is pointing inside, which is minus I, okay? Minus 4i. And this will give me, okay, sorry, this is 16, 4 times 4 is 16, not 8. I was adding them somehow, but it's minus 16. And here it will be, this j dot I will give me 0, I dot I will give me 1, and minus 4 will give me plus 16 Newton per Coulomb meter square, okay? That's the front face and the back face. Now we go to the right face, phi right, which is this face here. I'm talking about this face, the right face. Follow with me, my son, and the right face. So here, again, minus 4i plus 8j dot what? Dot which vector A? Vector A is pointing in this direction for this face. It will be 4j. Okay, so I dot j will give me 0, j dot j will give me 1. So this will be 32 Newton per Coulomb meter square. Okay, 32 per Coulomb meter, and it's a plus sign. Okay, plus sign. We can put a plus sign here. So the flux is positive on this side. Okay, now we go to the left face, phi left, and calculate that flux from there. The electric field again is the same, minus 4i plus 8j dot what? Dot 4 for the magnitude of the area, and it will be minus j here, okay? There will be minus j, and this will give you minus 32 Newton per Coulomb meter square. How about the flux through the top face? The top face, there's no electric field component which crosses the top face. This is 0, and also the bottom face, the bottom face, the electric field doesn't cross them. There's no E actually crossing. You see, there's no K component crossing these two faces, the top and bottom, and the flux through that will be 0. So let's calculate now the net flux then. The flux net, which is the sum of all these fluxes. You have plus 16 cancel minus, plus 16 cancel and minus 16, and plus 32 cancel the minus 32 here, and you get 0. Flux net will be 0, and this is equal Q enclosed over epsilon 0. Therefore, it means that Q enclosed is how much? It is also 0. So there's no charge enclosed inside this this surface here. This is a cube. There's no charge inside. The electric field here actually is coming from outside. And remember, my son, we did this before. If you have a closed surface, any closed surface, okay, any closed surface, and you have a charge outside, and you have an electric field crossing the surface, okay, electric field crossing the surface, you have the flux entering equal to the flux leaving. The flux here through the surface is equal to what? Is equal to 0 because there's no charge enclosed. This is the same problem here. This electric field is actually created by a charge which is outside. Okay, so the net flux is 0, and there is no charge enclosed in this surface, in this cubical Gaussian surface. Thank you. Okay, this is example number 5 related to electric flux through electric flux. Now this example, it says the figure shows an infinitely long line. Of course, it's not showing in the infinite because it has to go through these directions like this, and it's a line charge, so it has lambda, which is a Q over L. It's linear charge density. Okay, a charge having a uniform charge density per unit length lambda. The line lies at a normal distance from a center of a sphere. The sphere is not there. It's a Gaussian sphere. Okay, it's a Gaussian surface. It has a shape of a sphere. Here they are showing only a circle, but actually this is a sphere. Okay, it says a sphere of radius r, and remember, notice that r is the radius, and this is d is a perpendicular distance between this line and the center of the sphere. Okay, so you have the center of the sphere here, and you have the line 90 degrees here. You can see here 90 degrees. Okay, He wants the electric flux through the surface of the sphere resulting from this line distribution, okay, this charge distribution. You want the flux. So the flux again is Q enclosed over epsilon 0. What is a charge enclosed? Is look at this. The only part of the charge which is enclosed is this part here, because this charge here and this charge here are outside this Gaussian surface. This is a sphere, okay? You can write it. You can show that this is a sphere, okay, three-dimensional. So this charge here going to this side is outside. This is outside. So I'm going to take only this charge here, this part, okay, this charge. So I'm going to call it lambda L over epsilon 0. So what is L? L is this length here, the length from here to here. That's the L I'm looking for, okay? Which is the length of the charge inside this Gaussian surface, okay? So you can see that by using Pythagoras, okay, we can see that this is a right triangle. We have a right triangle, okay? This is R, this is L, D. This is D, okay? Okay, and this is L over 2, because this is the center of the sphere. Okay, sorry, the center is here of the sphere. So this is, they have this part and you have the other part. I'm showing only one part, okay? And this is the 90 degrees here. That's the 90 degrees. So how much is L over 2? Okay? How much is L over 2? L over 2 is square root of R squared minus D squared. Okay? So L will be, L what that I want, will be 2 square root of R squared minus D squared. So I'm going to put it there, okay, to find the flux. So the flux will be lambda 2 square root of R squared minus D squared over epsilon 0. And this is the final answer, okay? That's the final answer we are looking for. In this problem, there are no numbers. He is giving you the answer in the exam is a multiple choice, and one of the answers is this, is 2 lambda square root of R squared minus D squared over epsilon 0. Thank you.